Beneath shadowed forests and across sun-scorched floodplains, colossal hunters stalked their prey with ruthless precision, shaping the very rhythm of prehistoric life. Long before humans, Earth belonged to predators whose teeth, claws, and cunning defined survival itself. From sail-backed synapsids to saber-toothed mammals, these apex hunters carved empires of fear across land, air, and sea, leaving echoes that reverberate through evolution. In every roar, chase, and ambush, the story of dominance unfolds, revealing the brutal ingenuity of life. Step into a world where the hunt dictated existence, and witness the rise of the first true superpredators. Abyssal terror, the dawn of giant sharks. Beneath the undulating surface of the early Cenozoic oceans, a predator unlike any the world had yet known began to take shape. The waters shimmered with schools of fish, unaware that the lineage of early megatoothed sharks, ancestors of the colossal megalodon, was evolving toward unprecedented dominance. Fossils recovered from Eocene strata, particularly in the temperate seas of what is now Europe and North America, reveal serrated teeth no longer than a human hand, but already adapted for cutting through thick flesh, foreshadowing the immense killing machines to come. Each jaw fragment speaks to an evolutionary experiment in predation, a gradual scaling from nimble hunters to apex titans that would soon rule the oceans with unmatched ferocity. Paleontologists studying the Otodus obliqua species, one of the earliest megatoothed sharks, have identified a body plan optimized for both speed and power. Skeletons, reconstructed from rare vertebrae and cranial fragments, indicate a streamlined, torpedo-shaped body reaching lengths of 6 to 8 meters, agile enough to chase schools of bony fish, yet sturdy enough to tackle marine mammals that were emerging in parallel evolutionary timelines. Unlike modern sharks, which rely primarily on bursts of acceleration, these early predators had muscular tails and vertebral column flexibility, suggesting sustained swimming endurance, an adaptation that allowed them to patrol vast territories and exploit food sources across continental shelves. Teeth provide one of the clearest windows into the predatory evolution of these giants. Early Otodus specimens display a broad triangular crown with fine serrations along the edges, a morphology remarkably similar to that of Carcharocles megalodon, yet smaller and less robust. Microscopic wear patterns indicate repeated puncturing and slicing of flesh, rather than mere scavenging, suggesting that active hunting dominated their feeding strategy. Interestingly, isotopic analysis of tooth enamel reveals shifts in ocean temperature tolerance, showing that these sharks gradually expanded their range from warmer equatorial waters into cooler temperate zones, marking a significant step toward global dominance in the oceans. Fossil evidence also hints at a profound ecological impact. Bite marks on the vertebrae of early whales such as Basilosaurus and Dorudon indicate that these sharks were among the first predators capable of preying upon fully aquatic mammals. This predatory pressure likely drove early cetaceans to evolve faster swimming capabilities and defensive strategies, creating a dynamic predator-prey arms race that echoes the evolutionary stories of terrestrial ecosystems. The oceans were transforming into arenas where size, strength, and speed determined survival, and these emerging sharks were quickly positioning themselves at the apex. The Eocene seas were not a void, but a complex network of ecological niches, and the early megatoothed sharks were beginning to exploit every available resource. Fossil assemblages indicate cohabitation with large, bony fish, primitive rays, and smaller shark species. Yet the emerging Otodontidae were clearly the dominant hunters. Their rapid growth rates, inferred from vertebral ring counts, suggest that juveniles could reach lengths exceeding 3 meters within a few years, a remarkable pace that would have enabled them to compete with adult predators for food while minimizing vulnerability to larger threats. Paleoceanographic studies provide further context for their rise. During the Paleogene period, rising sea levels created extensive shallow continental shelves rich in marine biodiversity, offering abundant hunting grounds for predatory sharks. Warm, nutrient-rich currents encouraged blooms of plankton, which in turn supported schools of fish and cephalopods, forming a robust food web that early mega-toothed sharks could exploit. Fossilized stomach contents from later relatives suggest a diet composed not only of fish, but also of pinnipeds and other marine mammals, implying that these adaptations were already taking shape in their ancestral forms, a critical step toward achieving apex status. The skeletal morphology of these sharks reveals yet another facet of their evolutionary ingenuity. Vertebral centra exhibit pronounced calcification, allowing for powerful tail propulsion, while the pectoral fins, attached with robust girdles, suggest a capacity for precise maneuvering in three-dimensional aquatic space. Computed tomography scans of fossilized cranial remains show expanded olfactory bulbs, indicating that smell was likely a primary sense in locating prey over vast distances. This combination of endurance, swimming, acute sensory perception, and formidable biting apparatus underscores the evolutionary pressures that shaped their dominance in the marine realm. Even minor anatomical variations provide insight into their predatory strategies. Comparative studies of tooth serration density suggest that northern populations, inhabiting cooler waters with slower prey, developed coarser serrations for tearing, whereas equatorial populations retained finer edges optimized for slicing agile fish. Such evidence points to early intraspecific specialization, demonstrating that these sharks were not merely larger versions of smaller predators, but sophisticated hunters fine-tuned to their environmental conditions. Fossil evidence also hints at social, or at least territorial, behaviors. Large assemblages of teeth concentrated in specific locations imply repeated hunting in favored feeding grounds or possible competition among multiple individuals. While direct proof of pack hunting remains elusive, these patterns suggest a complex ecological awareness that extended beyond mere opportunistic feeding. Such dominance over space and prey highlights the strategic intelligence emerging in these early superpredators, a precursor to the even more formidable megalodon that would later terrorize oceans worldwide. As the lineage of early megatoothed sharks evolved through the Oligocene into the Miocene, body sizes expanded dramatically, approaching lengths of 15 meters or more, and jaws capable of exerting pressures exceeding tens of tons per bite. The evolutionary trajectory from nimble hunters to these colossi represents one of the most extreme examples of predatory adaptation in Earth's history, illustrating how environmental opportunity, sensory refinement, and anatomical innovation converged to create apex dominance. Fossils from North America, Europe, and Africa collectively paint a picture of a predator that was not only formidable, but virtually unrivaled in its habitat. The story of these abyssal terrors is more than a tale of size and teeth. It is a narrative of ecological transformation. As they claimed the seas, they reshaped prey species, influenced marine evolution, and established a blueprint for apex predation that would echo for millions of years. From these oceans, the stage was quietly being set for life to assert itself on land, where the first terrestrial superpredators would evolve, bringing with them their own strategies, ferocity, and dominance. In this way, the rise of the giant sharks forms both a prelude and a mirror, illustrating the relentless drive toward apex status in every corner of the prehistoric world. Lurkers of the swamp, the age of giant crocodiliforms. The rivers of the late Cretaceous were silent stages for predators of unimaginable power, their surfaces glinting under the sun, while the water below concealed shapes of immense threat. Among the reeds and submerged logs, Deinosuchus and its kin lurked, colossal crocodile-like hunters that could surpass 10 meters in length, each movement deliberate, yet brimming with lethal potential. Fossils recovered from the southeastern United States, particularly in regions now known as North Carolina and Montana, reveal vertebrae the size of basketballs and teeth as long as a human forearm, serrated like the edge of a saw, and capable of crushing bone. These ancient swamps were not mere backwaters. They were arenas where size, stealth, and raw power combined to create apex dominance, rivaling even the ocean's mega-toothed giants. Fossilized teeth embedded in hadrosaur and ceratopsian bones provide tangible evidence of ambush predation, showing puncture wounds and crushing patterns that could only have been inflicted by immense jaw strength. Biomechanical reconstructions estimate that adult Deinosuchus could exert bite forces exceeding 18,000 newtons, enough to sever vertebrae or puncture thick rib armor. This lethal capability allowed them to dominate riverbanks and estuarine habitats, preying on dinosaurs that ventured too close to water. Their hunting strategy was not one of speed but of patience, a deadly blend of motionless waiting and sudden, explosive strikes that left little chance for escape. Muscular tails and armored hides made these predators both powerful swimmers and resilient hunters. Vertebral analyses indicate a combination of flexibility and propulsion capable of bursts of acceleration in ambush, while thick osteoderms along the back protected against struggles with prey or occasional intraspecies combat. This balance of offense and defense made giant crocodiliforms exceptionally well suited for their aquatic ambush lifestyle, an evolutionary niche that had no equivalent among terrestrial dinosaurs of the same period. Fossil discoveries in sedimentary deposits suggest that these rivers, rich in fish, turtles, and occasional terrestrial stragglers, offered abundant prey, supporting multiple large individuals within the same ecosystem. Sediment cores and paleogeographic reconstructions further illuminate the world to these predators dominated. Shallow estuaries and winding river channels created complex habitats filled with submerged vegetation and driftwood, providing perfect cover for ambush attacks. Evidence of seasonal flooding suggests that prey movements were often predictable, allowing Deinosuchus to exploit natural bottlenecks. Teeth found far upstream in regions now disconnected from the coast indicate a capacity for long-distance swimming, enabling territorial expansion and interpopulation encounters that may have included displays of dominance or competition for prime hunting grounds. Bite force estimates are supported not only by skeletal analysis, but also by damage observed in fossil prey. In addition to crushing dinosaur bones, fossilized turtles bear deep gouges from serrated teeth, illustrating versatility in diet. The jaw mechanics of these predators suggest a combination of rapid closure and sustained pressure, allowing them to hold struggling prey underwater until exhaustion. This technique is mirrored in modern crocodilians, but amplified to an extraordinary scale, providing insight into how Deinosuchus achieved apex status in rivers and swamps. Comparative anatomy of the limbs suggests a fascinating duality. These animals were capable of terrestrial movement, though awkwardly, yet their primary hunting strategy remained aquatic. Limb placement and joint structure indicate that they could lunge onto riverbanks to ambush unsuspecting prey, or even traverse short distances between water bodies to maintain access to rich feeding grounds. Juvenile specimens show rapid growth, reaching several meters in a few years, highlighting a life history adapted to early predatory independence and ecological dominance from a young age. Predation pressures shaped not only individual prey species but entire ecosystems. Dinosaurs, early mammals, turtles, and fish all adapted behaviors in response to these riverine hunters. Herding behavior in hadrosaurs and movement toward drier floodplains may have been influenced by crocodiliform presence, while the evolution of armored shells and spiny defenses in aquatic reptiles can be seen as a direct response to ambush predation. Fossilized footprints and trackways suggest that even apex predators faced competition, as multiple large individuals occasionally frequented the same hunting grounds, implying territorial disputes and complex social interactions. Cranial sensory adaptations of Deinosuchus reveal evolutionary refinements similar to those of modern crocodilians, but on a scale befitting their size. Pressure-sensitive pits along the jaws, enhanced vision adapted for low-light conditions, and possibly acute hearing allowed them to detect the faintest movements of prey beneath murky waters. This sensory precision, combined with patience and brute force, created predators that were both physically and behaviorally formidable, demonstrating that apex status is as much about strategy as size. Evidence from multiple continents, including Africa and Asia, indicates that large crocodiliforms evolved convergently, suggesting that similar ecological pressures consistently favoured immense ambush predators in freshwater environments. These giant hunters provide a lens into the dynamics of late Cretaceous rivers, where predation shaped population distributions, influenced migratory patterns, and controlled the flow of energy through ecosystems. Each fossil tells a story of tension, patience, and explosive violence, illustrating a continuity of apex predation strategies from ancient seas to riverine habitats. As the late Cretaceous rivers teemed with life, the presence of these ambush predators transformed swamps and estuaries into crucibles of ecological adaptation. The rise of Deinosuchus and its kin underscores a central theme of prehistoric survival. Apex status was not merely a matter of size, but the integration of patience, sensory precision, and mechanical power. Across continents and ecosystems, these giants established a template for terrestrial hunting that would resonate in the evolution of fully land-based predators. In the shadowed waters and sunlit banks of ancient rivers, the first hints of terrestrial predation were taking shape, a prelude to the speed, claws, and cunning that would soon dominate land itself. Raptors of the apex, Utah raptor unleashed. Shadows raced across sun-baked floodplains as claws met soil with startling precision, leaving faint impressions that would endure for millions of years. Utah raptor, a giant dromaeosaur of the early Cretaceous, dominated these landscapes with a blend of speed, agility, and intelligence, capable of taking down prey far larger than itself. Fossilized remains from Utah and surrounding regions reveal a predator exceeding 6 meters in length, with sickle-shaped claws on each foot and muscular forelimbs built for grappling. These raptors transformed the open plains into arenas where predatory efficiency determined survival, creating a tension between hunter and hunted that reshaped entire ecosystems. Embedded in ancient rock, fossilized talons tell a story of predation perfected through millions of years of evolution. The infamous killing claw, curved and serrated, was capable of slashing into thick hides and gripping struggling prey. Biomechanical studies suggest that this claw, paired with strong hind limb musculature, allowed Utahraptor to leap or pivot at high speed, combining brute strength with precise control. Such adaptations made the species a master of calculated attacks, demonstrating that apex predation on land required more than sheer size. It demanded coordination, precision, and timing. The bone structure of Utahraptor reveals powerful hindquarters capable of sudden acceleration over uneven terrain. Fossil reconstructions indicate elongated femurs and strong pelvic girdles, ideal for bursts of speed, as well as long metatarsals that provided spring-like leverage during pursuit. Unlike ambush predators in rivers and swamps, these terrestrial hunters relied on sustained activity, chasing down herbivorous dinosaurs such as iguanodontids and smaller sauropods. Their skeletal design reflects a predator optimized for rapid, dynamic motion, translating muscle power into explosive attacks that could topple prey many times their own weight. Serrated teeth etched into prey bones show a combination of slicing and gripping efficiency, revealing dietary habits that ranged from large herbivorous dinosaurs to smaller vertebrates. Microscopic analysis of tooth wear patterns suggests repeated puncturing and shearing, indicating both kill and consumption techniques were honed for maximum efficiency. The morphology of the jaws allowed for both tearing and holding struggling prey, illustrating an evolutionarily advanced system of predation unmatched by contemporaneous predators of similar size. Rapid growth patterns suggest juveniles could compete with smaller predators within a few years, rapidly attaining sizes sufficient for hunting independently. Histological studies of long bones reveal growth rings, indicative of fast maturation, a crucial trait in competitive early Cretaceous ecosystems. Juvenile Utahraptors may have hunted in smaller groups or targeted smaller prey, gradually scaling up their predatory strategies as they matured, a life history finely tuned for ecological efficiency and survival in a dynamic environment. Forelimbs, equipped with muscular grips, hint at grappling techniques for subduing massive herbivores. Fossilized arm bones display well-developed muscle attachment sites, suggesting powerful strokes capable of holding struggling prey in place, while the hind limbs and claws delivered lethal strikes. Such adaptations, coupled with the balance provided by a stiffened tail, demonstrate a sophisticated predatory toolkit where strength, dexterity, and speed converged into a single evolutionary marvel. Tracks preserved in mudstones capture fleeting movements, hinting at coordinated or territorial behavior across early Cretaceous floodplains. Parallel trackways suggest multiple individuals may have hunted in tandem or patrolled overlapping territories, implying social behavior or at least strategic interaction with other predators. These patterns also hint at complex predator-prey dynamics, as herbivorous species adapted migration and vigilance behaviors to avoid ambush by such highly capable hunters. Large optic lobes in the skull suggest advanced visual processing for high-speed hunting, allowing precise judgment during pursuit over uneven terrain. Combined with proprioceptive adaptations inferred from limb articulation, Utahraptor could anticipate prey movements, adjust its balance mid-stride, and execute rapid directional changes while maintaining lethal accuracy. These sensory refinements indicate that intelligence and motor control were central to apex predation, emphasizing that dominance was as much cerebral as it was physical. Claw curvature and limb articulation indicate evolutionary refinement for both attack and stability. The sickle claws were reinforced by bone geometry and tendon placement, enabling repeated high-force strikes without injury. Additionally, the forelimbs and tail worked in concert to stabilize the body during hunting maneuvers, creating a highly coordinated system that optimized both speed and strength. This combination of anatomical precision and biomechanical efficiency elevated Utahraptor above mere opportunistic predators, marking it as one of the earliest land-based apex hunters capable of taking down formidable prey. Prey behavior, from herd migration to defensive formations, reflects the ecological pressure of these predators. Fossilized trackways and bone beds indicate that iguanodontids and other herbivores modified movement patterns to avoid raptor ambushes, while evidence of defensive injuries suggests that these interactions were frequent and intense. The evolutionary arms race between predator and prey intensified across the floodplains, creating a dynamic ecosystem in which selective pressures shaped speed, awareness, and social behavior on both sides. Analyses of remains from diverse locations confirm consistent adaptation trends among dromaeosaurs worldwide. Utahraptor's size, claw mechanics, and hunting sophistication mirror evolutionary strategies seen in later relatives, demonstrating convergent trends toward large, agile, cooperative predation. These adaptations highlight the continuity of apex strategies, building on lessons from aquatic and swamp-based hunters while refining them for the unique demands of fully terrestrial environments. In open plains and fern-dotted valleys, these raptors sharpened a template of speed and cunning that foreshadowed the rise of tyrannosaurid titans, creatures whose combination of size, power, and strategy would eclipse all prior terrestrial hunters. The story of Utahraptor reminds us that apex predation is never static. It evolves in response to environment, prey, and competition. From the shadowed swamps to open floodplains, the relentless drive toward mastery, whether through stealth, patience, or agility, continued to shape life on land, setting the stage for the colossal rulers of the late Cretaceous plains. The king emerges, Tyrannosaurus rex. Dust swirled across the late Cretaceous plains as massive shadows approached from the horizon, the ground trembling under the weight of a predator unmatched in scale and presence. Tyrannosaurus rex, the ultimate apex hunter, commanded these landscapes with a combination of sheer size, lethal bite power, and sensory precision. Fossil evidence from Montana, Alberta, and the Dakotas reveals skulls measuring over 1 meter in length, with jaw musculature engineered to crush bone and rend flesh with terrifying efficiency. The open plains offered little cover for prey, amplifying T-Rex's dominance as it patrolled vast territories in search of food. Fossilized skulls reveal a jaw structure engineered for bone-crushing efficiency, with fused cranial bone supporting enormous bite forces. Biomechanical reconstructions estimate that T. rex could deliver between 35,000 and 57,000 newtons of force, sufficient to pulverize vertebrae or shatter armored limbs. This power allowed it to hunt massive, herbivorous dinosaurs such as ceratopsids and hadrosaurs, turning prey size into an advantage rather than a deterrent. Unlike the swift Utahraptor, T. rex relied on strategic placement, patience, and raw mechanical force to subdue its quarry. Teeth, some exceeding 30 centimeters in length, were serrated like steak knives, optimized for puncturing and slicing. Microscopic studies reveal wear patterns consistent with repeated bone crushing, indicating that T. rex could extract marrow as easily as muscle. Fossilized prey bones bearing these distinctive marks tell stories of predation and scavenging, demonstrating a predator that could both kill and efficiently consume even the largest herbivores. Each tooth was a precision tool, capable of dealing fatal damage with a single strike. Limb proportions indicate a predator designed for bursts of speed despite colossal mass. powerful hind limbs, combined with robust pelvic structures, provided acceleration over short distances, allowing T. rex to ambush or chase prey across open plains. Despite standing up to 6 meters tall and weighing over 7 tons, anatomical adaptations minimized energy expenditure during locomotion, suggesting a combination of stealth, endurance, and explosive strength. This blend of mobility and mass made it a versatile hunter, capable of both pursuit and surprise attacks. Evidence from fossilized trackways suggests territorial dominance and strategic hunting routes. Trails preserved in ancient mudstones reveal repeated passage across river crossings and floodplains, indicating habitual travel corridors and areas of concentrated predatory activity. These tracks, sometimes alongside juvenile specimens, hint at complex life histories, possibly including solitary hunting in adulthood, combined with overlapping territories shared among multiple individuals. Such behavior would have influenced prey movement patterns, creating cascading effects across entire ecosystems. Binocular vision and expanded olfactory lobes hint at acute sensory capabilities unparalleled among contemporary predators. The placement of the eyes allowed depth perception, crucial for judging distance during predatory strikes, while the olfactory system detected carcasses and live prey across kilometers. Neurological reconstructions of the brain case suggest heightened integration of sensory input, giving T. rex an unparalleled awareness of its surroundings, an evolutionary advantage that complemented its physical power and hunting strategy. Growth ring analysis indicates rapid juvenile development, preparing individuals for apex status within a few years. Fossilized long bones show evidence of accelerated growth, suggesting that young T. rex could quickly reach sizes sufficient to compete with smaller predators or tackle progressively larger prey. This rapid ontogeny ensured that each generation could assume ecological dominance and maintain continuity of apex predation across decades and millennia. Bone microstructure of T. rex reveals a network of vascular canals that suggests sustained metabolic activity beyond what is typical for reptiles. Recent histological studies indicate that T. rex may have maintained a level of metabolic efficiency closer to that of modern birds than cold-blooded reptiles, supporting prolonged activity during hunts or territorial patrols. These findings also hint at seasonal growth variations, where periods of abundant food allowed rapid skeletal expansion, while leaner times slowed growth. The combination of high metabolism and rapid growth would have been critical in reaching apex predator status within a relatively short lifespan, ensuring that T. rex could dominate ecosystems while juvenile cohorts matured swiftly. This physiological insight adds depth to our understanding of how the species sustained its size, strength, and predatory capabilities in a competitive environment. Bite marks on saber-toothed and hadrosaur bones provide direct evidence of predation and scavenging strategies. The distribution and orientation of these marks reveal repeated patterns, showing that T. rex employed a combination of ambush, pursuit, and opportunistic feeding. Analysis of healed wounds on prey fossils indicates that interactions were often prolonged and violent, reflecting the high-risk, high-reward nature of life at the top of the food chain. These behaviors underline the predator's ability to impact populations, drive evolutionary adaptations in prey, and control ecosystem dynamics. Skeletal adaptations of the pelvis and tail illustrate balance optimization for both locomotion and predatory maneuvers. A long, muscular tail acted as a counterweight to the massive head and torso, allowing rapid turns during pursuit or struggle. The fused vertebrae and robust hip structure distributed weight efficiently, enabling the colossal predator to maintain stability during bursts of activity. Such anatomical refinements were essential for managing the physical demands of predation at unprecedented scales. Pathologies preserved in fossils suggest combat with rivals or encounters with resistant prey, revealing the risks inherent to apex status. Fractured ribs, healed bite marks, and stress-induced bone growth illustrate violent interactions, whether with other T-Rex individuals or large herbivores defending themselves. These scars tell a story of an ecosystem shaped by competition, survival, and the relentless drive for dominance, emphasizing that even the mightiest predator faced constant challenges. Geographic distribution from North America provides insight into environmental adaptability and ecological dominance. Fossils from varied habitats, river valleys, coastal plains, and upland floodplains demonstrate that T-Rex could exploit a range of ecosystems. This versatility ensured consistent access to prey and reinforced its position at the apex, highlighting the evolutionary culmination of terrestrial predatory strategies refined over millions of years. In the shadow of these titans, ecosystems were reshaped, prey populations pressured, and evolutionary trends set into motion for the future. T. Rex represents the pinnacle of terrestrial predation, a creature whose combination of size, strength, and sensory acuity epitomized apex dominance. While it ruled the late Cretaceous plains with unmatched authority, its reign also evokes the deep history of terrestrial predation, echoing strategies first tested in earlier epochs. From cunning raptors to colossal tyrants, the relentless drive to master land-based hunting continues to reveal the profound ingenuity of evolution, setting the stage for reflections on the earliest predators that shaped terrestrial food chains millions of years ago. The Permian nightmare, Dimetrodon and its kin. Early morning mists clung to arid riverbeds as sail-backed hunters emerged from shadowed thickets, their silhouettes stretched across sand and clay. Long before the age of dinosaurs, Dimetrodon and its kin dominated the Permian landscape, apex predators whose form and behavior shaped ecosystems across vast floodplains and swamp margins. Fossils from North America reveal skulls up to 1/2 meter long, equipped with robust jaws capable of tearing through armored amphibians and early reptiles. These predators embodied evolutionary experimentation, refining strategies that would echo millions of years later in dinosaurian hunters, illustrating the deep roots of apex predation on land. The jaws of Dimetrodon, serrated and powerful, hint at a predator capable of crushing and slicing simultaneously. With conical teeth interspersed with blade-like serrations, these synapsids could subdue a range of prey, from agile amphibians to burrowing reptiles. Biomechanical reconstructions showed jaw muscles arranged for maximum force, allowing Dimetrodon to overpower creatures of comparable size while minimizing the risk of injury. Each strike was precise and deadly, a reflection of evolutionary pressures that rewarded efficiency in a harsh, competitive environment. Teeth of varying shapes reveal specialization for slicing, crushing, and processing different types of prey. The front incisors were ideal for seizing, while the middle and rear teeth performed shearing and crushing, suggesting a versatile feeding strategy. This dentition allowed Dimetrodon to exploit multiple ecological niches, maintaining dominance even as competitors evolved. Fossilized stomach contents, though rare, provide additional evidence of dietary breadth, confirming these synapsids as generalist apex hunters with lethal efficiency. Skeletal remains suggest muscular forelimbs and sprawling postures adapted for ambush predation. Limbs were stout and powerful, enabling quick lunges from concealed positions among rocks, fallen logs, or riverbanks. The combination of low-slung posture and explosive muscle contractions made sudden strikes possible, allowing predators to capture prey before it could escape. This ambush-centric hunting contrasts sharply with the pursuit-based predation of later theropods, highlighting the diversity of evolutionary solutions to apex status. The iconic dorsal sail, formed by elongated neural spines, may have regulated body temperature or signaled dominance within species. Thermoregulatory hypotheses suggest that blood flowing through the sail allowed rapid heating or cooling, providing a metabolic edge during activity or rest. Alternatively, the sail may have served as a visual signal for mating, territorial disputes, or intimidation, adding a layer of behavioral complexity rarely appreciated in early terrestrial predators. Fossils showing varying sail sizes hint at sexual dimorphism or ontogenetic changes, revealing nuanced ecological and social roles. Detailed study of Dimetrodon remains indicates that some individuals experienced seasonal shedding of their scales, hinting at physiological and behavioral adaptations previously unrecognized. This cyclical scale shedding may have helped regulate body temperature, remove parasites, or signal reproductive readiness, providing a multi-purpose advantage in fluctuating Permian climates. Additionally, variations in scale, texture, and size across different body regions suggest that Dimetrodon could have used visual cues to communicate with rivals or potential mates, adding a social or signaling dimension to their predatory lifestyle. These subtle biological traits reveal that, beyond jaws, teeth, and sails, sail-backed synapsids possessed a suite of adaptations that enhanced survival, efficiency, and dominance within their ecosystems. Such details expand our understanding of Permian predators as highly specialized and dynamic organisms, not merely as static, primitive hunters. Trackways preserved in sandstone suggest solitary hunting behaviors across vast, open Permian landscapes. Isolated footprints, often accompanied by sudden directional shifts, indicate ambush strategies and territorial patrolling. Unlike later social hunters, these apex synapsids relied on stealth, strength, and environmental mastery, shaping prey populations through targeted predation rather than group coordination. Such behaviors contributed to an early balance between predator and prey that echoed throughout Permian ecosystems. Paleoecological reconstructions show these synapsids coexisted with amphibians, early reptiles, and invertebrates, forming complex predator-prey dynamics. Fossil assemblages reveal diverse food webs, where Dimetrodon influenced the evolution of defensive strategies among herbivores and smaller carnivores alike. This ecological pressure fostered adaptations such as burrowing, nocturnal activity, and body armor, illustrating that apex predation drives evolutionary innovation as strongly as it reflects mechanical superiority. Bone histology suggests growth rates that balanced energy expenditure with survival, reflecting metabolic strategies distinct from later theropods. Analysis of growth rings in long bones shows periods of accelerated development followed by slower phases, possibly correlated with seasonal resource availability. These growth patterns allowed individuals to reach functional size quickly while avoiding excessive energy costs, demonstrating a physiological sophistication that supports their apex predatory role. Evidence of bite marks on fossil prey reveals lethal interactions, sometimes leaving healed wounds indicative of repeated predation attempts. Amphibian and reptile bones exhibit punctures consistent with Dimetrodon's teeth, showing both successful kills and survival of near misses. Such evidence provides a rare glimpse into ecological interactions, highlighting the high-stakes nature of survival at the top of the food chain during the Permian. Geographical distribution across what is now North America highlights the ecological dominance of sail-backed synapsids during the mid to late Permian. Fossils have been uncovered in Texas, Oklahoma, and New Mexico, indicating a broad range of adaptation to floodplains, river margins, and semi-arid habitats. Their widespread presence underscores their effectiveness as apex predators and their ability to shape prey populations across diverse environments. Comparative analysis with later therapsids illustrates evolutionary experimentation in predatory strategies that prefigured future apex predators. Dimetrodon and its relatives demonstrate how selective pressures in early terrestrial ecosystems drove innovations in dentition, locomotion, and behavior, setting a blueprint that later predators, including dinosaurs and mammalian ancestors, would refine. This evolutionary continuity emphasizes that apex predation is a recurring theme in Earth's history, expressed differently in each era according to ecological constraints. Dominating floodplains and swampy edges in the Permian, these predators set the stage for the emergence of apex hunters in the Triassic seas that would continue the relentless saga of predation. The story of Dimetrodon reminds us that dominance is never absolute, but must be continually earned through adaptation, strategy, and environmental mastery. From sail-backed synapsids to tyrannosaurid titans, the evolutionary narrative of apex predation is a testament to the enduring ingenuity of life, connecting deep terrestrial history to the creatures that would eventually terrify oceans in the Triassic. Sea behemoths, the ichthyosaurs and their prey. Sunlight fractured through turbulent Triassic waves as ichthyosaurs glided with predatory intent, their streamlined bodies slicing effortlessly through the liquid world. These dolphin-like reptiles were apex hunters of the oceans, evolved to pursue and capture prey with unmatched speed and precision. Fossil evidence and biomechanical reconstructions reveal a perfect marriage of form and function. Long, tapering bodies, crescent-shaped tails, and rigid vertebrae allowed for sustained bursts of velocity, transforming these marine reptiles into relentless hunters. Streamlined bodies, reinforced vertebrae, and crescent-shaped tails transformed them into unmatched swimmers capable of dominating vast stretches of open water. Unlike terrestrial predators, ichthyosaurs relied on hydrodynamic efficiency and muscular power rather than brute force alone. Water currents and thermoclines shaped the hunting strategies of ichthyosaurs in ways rarely appreciated in the fossil record. Reconstruction suggests they exploited temperature gradients to ambush prey from below, using subtle differences in water density and light refraction, while some size-sorted fossil assemblages hint at early social or spatial hunting strategies. Eyes adapted for low-light vision allowed hunting at depth and tracking prey across open water, giving ichthyosaurs an advantage over cephalopods and fish that relied on camouflage or darkness for protection. Some species possessed eyes measuring over 20 centimeters in diameter, among the largest in the animal kingdom, allowing them to detect movement across dimly lit oceanic zones. Beyond eyesight, ichthyosaurs may have relied on an acute sense of proprioception and vibration detection along their elongated bodies. Neurological reconstructions suggest they were sensitive to pressure changes, enabling them to detect fleeing prey or navigate turbulent currents with precision. Conical, interlocking teeth reveal specialization for gripping slippery cephalopods and fish, ensuring that once caught, prey could not escape. Jaw morphology indicates rapid closure and strong bite forces tailored to hold squirming animals, preventing them from wriggling free during pursuit. Variations in tooth size across species suggest dietary partitioning, minimizing competition in rich but crowded Triassic seas and allowing multiple ichthyosaur species to coexist. Remains found within abdominal cavities indicate a varied diet of ammonites, fish, and even smaller reptiles, confirming that ichthyosaurs were opportunistic hunters capable of adapting to prey availability. Fossils with partially digested cephalopod shells demonstrate both the efficiency and selectivity of their feeding habits. These preserved meals offer rare, tangible insights into predator-prey relationships in deep-time marine ecosystems, underscoring the crucial role these apex predators played in shaping their environment. Fins and limbs were finely tuned for rapid maneuvering, enabling sudden bursts of speed during chases. Pectoral fins functioned like hydroplanes, providing lift and directional control, while the dorsal fin and tail stabilized movement at high velocity. This combination allowed ichthyosaurs to execute precise turns and ambush maneuvers, cornering prey in confined spaces or executing sustained pursuits across open water. Their locomotion represents a convergence of evolutionary innovation, paralleling modern dolphins and predatory fish in form and function. Insights drawn from ichthyosaur skeletal chemistry indicate clues about the ancient ocean temperatures and migratory patterns they endured. Isotopic ratios of oxygen and carbon in their remains indicate seasonal movements across warmer and cooler waters, suggesting that some ichthyosaurs were highly migratory, traveling hundreds of kilometers to follow prey or breeding grounds. Trace elements further reveal differences in diet and habitat preference between species, highlighting ecological niche specialization within the same oceanic environments. These geochemical signatures provide rare insights into the lives of these predators beyond skeletal anatomy, showing how physiology, behavior, and environmental pressures intertwined to maintain their apex status in complex Triassic seas. Histological analysis of bones suggests rapid growth and early acquisition of apex status, allowing young ichthyosaurs to become effective hunters quickly. Growth rings indicate periods of accelerated skeletal expansion, often correlated with seasonal abundance of prey, highlighting a dynamic interplay between physiology and ecological opportunity. Fossils of gravid females reveal live birth, a rare adaptation among reptiles. Embryos preserved in utero show that ichthyosaurs were viviparous, allowing fully aquatic reproduction without the need to return to land. This adaptation, coupled with rapid growth, ensured they could maintain apex status across diverse marine ecosystems. Anatomical parallels with dolphins and modern predatory fish showcase remarkable evolutionary convergence, demonstrating that natural selection repeatedly favors similar solutions for apex predation in aquatic environments. Streamlined forms, powerful tails, and efficient locomotion evolved independently across distant lineages, reflecting fundamental physical principles of marine hunting. These parallels provide a bridge for understanding prehistoric marine ecosystems in terms that resonate with contemporary marine biology. Marks etched into prey skeletons reveal stories of stealth, speed, and aquatic predation. Fish and ammonite fossils display punctures and scratches that correspond precisely with ichthyosaur dentition, capturing interactions that occurred millions of years ago. Each preserved wound speaks to the precision of attacks, the intensity of pursuit, and the role of predation in driving evolutionary adaptations among prey species, from improved defense mechanisms to altered behavior patterns. Fossil distribution across Europe, North America, and Asia confirms their dominance in Triassic oceans, spanning tropical and temperate marine environments. This broad geographic range demonstrates their adaptability to diverse ecological conditions and underscores the success of their specialized anatomy and hunting strategies. Ichthyosaurs became a defining feature of the Triassic seas, shaping both food webs and evolutionary trajectories for other marine organisms. Predator-prey interactions within these seas illustrate evolutionary arms races, shaping both marine ecosystems and future lineages. The pursuit and evasion dynamics observed in the fossil record suggest that ichthyosaurs not only controlled prey populations, but also indirectly influenced the evolution of other marine reptiles and cephalopods. These interactions highlight the complexity and sophistication of ancient ecosystems, where apex predators like ichthyosaurs drove both survival and innovation beneath the waves. Meanwhile, terrestrial predators were simultaneously evolving strategies to dominate their own ecosystems, establishing a dual theatre of apex competition that would continue for millions of years. The story of ichthyosaurs reminds us that the drive for predatory mastery is universal, whether under sunlit oceans or on sun-drenched plains. In observing these sea behemoths, we witness the continuity of evolutionary ingenuity. Apex predation reshapes life across time and space, whether on land or in the ever-shifting theatre of the Triassic oceans. Terrestrial titans, Postosuchus, and the Triassic archosaurs. On the sun-baked floodplains of the late Triassic, Postosuchus moved with a calculated menace, each step deliberate yet ready to explode into sudden action. Its long, muscular limbs supported a semi-upright posture, allowing it to sprint and pivot with uncanny precision, an ideal combination for ambushing herbivorous prey along meandering rivers. The sprawling plains, dotted with cycads, horsetails, and ferns, provided both cover and hunting ground, turning the Triassic floodplains into arenas where survival demanded both strength and strategy. Fossil evidence suggests that these predators were capable of navigating dense vegetation and crossing shallow waterways, exploiting terrain as skillfully as their prey avoided them. Unlike sprawling crocodilians, Postosuchus could support its weight above the ground, reducing drag and increasing stamina for sustained pursuit. Its tail functioned as a dynamic counterbalance, stabilizing sudden changes in direction and delivering subtle propulsion during lunges, an integration of biomechanics that ensured apex dominance. Combined with agile forelimbs and clawed digits, this predator could pin struggling prey while maintaining balance on uneven terrain, a versatility that gave it an edge in both open plains and riverine corridors. Skull morphology, reinforced with bone ridges and serrated teeth, reveals predation built for crushing prey with efficiency and precision. Teeth measuring up to 10 centimeters in length, paired with powerful jaw muscles, enabled Postosuchus to pierce and sever flesh rapidly. Bite force reconstructions indicate a predator capable of dispatching animals larger than itself, from armored atosaurs to early sauropodomorphs, reflecting an apex predator whose influence shaped the behavior and evolution of contemporaneous herbivores. Traces preserved in fossilized trackways indicate not just speed, but strategic ambush patterns along riverbanks, with multiple sets of footprints suggesting calculated approaches to hunting grounds. The alignment of tracks with paleo rivers also suggests that Postosuchus understood and exploited the terrain, striking where prey was most concentrated. These traces hint at territorial behavior, possible patrol routes, and seasonal hunting corridors, revealing a complexity of behavior rarely preserved in the fossil record. Variations in skeletal and dental morphology imply that juveniles and adults may have hunted differently, suggesting complex, intraspecific ecological roles. Smaller, younger Postosuchus may have targeted faster, more elusive prey or scavenged from adult kills, while mature individuals dominated larger herbivores. This division of ecological labor would have minimized intraspecific competition and allowed the species to fully exploit the resource-rich Triassic floodplains, illustrating a nuanced predator-prey dynamic seldom captured in fossilized ecosystems. Evidence from differential bone wear and size variation across populations suggests that juveniles may have practiced learning behaviors, refining their hunting techniques in the shadow of adults. However, the upright limb posture, enhanced speed, and terrestrial agility distinguish Postosuchus from modern relatives, revealing a lineage experimenting with forms that would later culminate in theropod giants. The combination of endurance, mechanical leverage, and strike precision suggests a predator capable of adapting its hunting strategy to a wide variety of prey, an evolutionary versatility that helped it maintain apex status over millions of years. Paleo-environmental reconstructions show rivers, lakes, and seasonal floods influencing prey availability, forcing predators to adapt to a fluctuating landscape. High water seasons may have concentrated herbivores along shrinking shorelines, creating hunting hotspots, while dry periods dispersed them across parched plains, demanding versatility and patience. Postosuchus thrived in this dynamic environment, showcasing the importance of behavioral flexibility alongside physical prowess in apex predation. Sedimentological studies reveal mudflats and braided river channels that likely funneled herbivores into predictable paths, allowing Postosuchus to exploit environmental bottlenecks with lethal efficiency. Isotopic analyses of bones hint at migratory behaviors or range variations across floodplains. Subtle differences in oxygen and carbon isotopes suggest some individuals moved seasonally following concentrations of prey or accessing optimal breeding sites. Such findings underscore the sophistication of Triassic predators, whose survival depended not just on brute strength, but on an understanding of ecological patterns across vast and variable landscapes. When combined with fossil evidence of prey distribution, these data suggest Postosuchus could strategically adjust hunting routes to maximize encounters, demonstrating a level of environmental awareness previously underappreciated in Triassic archosaurs. Predation scars on herbivorous archosaurs preserve evidence of Postosuchus's hunting success, with punctures and healed wounds offering glimpses of encounters frozen in fossilized time. These marks reveal selective targeting of soft tissues and strategic strikes to immobilize prey efficiently, confirming long-held theories about their role as apex predators. The scars also hint at evolutionary pressures exerted on prey species, driving adaptations like enhanced armor, agility, and behavioral vigilance. In some cases, patterns of repeated scarring suggest territorial disputes or predation learning curves, revealing the complex interplay between predator and prey across generations. Morphological adaptations indicate a blend of endurance and explosive power, ideal for apex status in a predator-rich ecosystem. From reinforced limb joints to a flexible yet muscular tail, every aspect of its anatomy reflects natural selection, favoring both ambush efficiency and sustained pursuit. Postosuchus represents a peak in archosaur design, bridging the gap between smaller, opportunistic predators and the gigantic theropods that would follow in later periods. Its sensory acuity, likely keen smell and vision, further amplified its hunting capabilities, allowing it to detect subtle environmental cues and prey movements that might escape other predators. Concurrently, smaller predators and prey species evolved in response, shaping a complex Triassic ecosystem where every movement was part of a dynamic, interdependent network. The presence of Postosuchus likely influenced habitat choice, reproductive strategies, and social behaviors in surrounding species, revealing that apex predation is as much about ecological influence as direct consumption. This interplay of predator and prey drove evolutionary innovation across floodplains, forests, and riverbanks alike, creating a crucible where life continually adapted to the pressures of predation. Ultimately, Postosuchus exemplifies the escalating scale of terrestrial predation, foreshadowing the emergence of gigantic theropods in the Jurassic. Its reign demonstrates that apex status depends not solely on size, but on the integration of anatomy, strategy, and environmental awareness. From the rivers and floodplains of the Triassic, we witness the evolutionary prelude to the colossal land predators that would dominate for tens of millions of years, an enduring testament to life's relentless drive toward mastery of every ecological niche. The stage is now set for even greater terrestrial titans, whose sheer size and ferocity would redefine apex predation across the Mesozoic landscapes. Colossus of the Jurassic, Allosaurus rex. Through dense stands of conifers and cycads, Allosaurus threaded the undergrowth with surprising stealth, its massive frame betraying little of the explosive power coiled within. The dense Jurassic forests, with ferns carpeting the ground and ginkgos swaying in the wind, offered both concealment and opportunity, turning every shadow into a potential ambush point. Here, the predator honed a balance between brute force and calculated precision, stalking juvenile sauropods or injured stegosaurs along riverbanks, demonstrating that apex status was as much about strategy as sheer size. Its skull, equipped with serrated teeth and reinforced bone ridges, was designed for tearing through flesh and crushing bone alike. Individual teeth, measuring up to 7 centimeters, show microscopic wear patterns indicating repeated use on resistant tissues, including armored plates and thick hide. Paleontologists reconstruct a jaw capable of delivering a powerful shearing force while remaining agile enough for repeated bites in quick succession, highlighting the dual demands of strength and precision that defined Allosaurus predation. Additional cranial adaptations, such as flexible joints between skull bones, allowed for slight independent movement, increasing the effectiveness of biting angles during combat with larger prey. Limbs adapted for rapid acceleration allowed bursts of speed that compensated for its massive frame, with hind limbs displaying elongated metatarsals and robust musculature. Such adaptations made it capable of short, explosive sprints, enabling surprise attacks on unsuspecting herbivores and rapid repositioning during group hunting, if such behavior occurred. Combined with semi-flexible forelimbs tipped with recurved claws, Allosaurus could stabilize prey and maintain lethal control during close encounters, a predator refined for the chaotic energy of forested hunting grounds. Fossilized injuries on prey species hint at both targeted attacks and opportunistic scavenging, revealing a nuanced ecological role. Bites on juvenile sauropods and stegosaurs demonstrate predation strategies that focused on weak points, while healed scars suggest repeated encounters that shaped evolutionary responses in prey populations. The predator's presence influenced not only individual survival, but also reproductive and migratory behaviors, reshaping entire Jurassic communities through both direct predation and indirect ecological pressure. Combined with the forest's variable terrain, these interactions show that hunting success depended on adaptability and acute environmental awareness, not solely brute strength. The muscular tail served as a dynamic counterbalance, aiding agility during rapid maneuvers through undergrowth and across uneven terrain. Its vertebral morphology, reinforced with elongated neural spines and interlocking zygapophyses, supported swift lateral movements and minimized energy loss during pursuit. When combined with forelimb dexterity, this tail structure created a fluid, kinetic predator capable of making split-second adjustments, a living embodiment of evolutionary optimization for terrestrial hunting. Observing the adaptations of smaller theropods exposes an evolutionary trend toward larger, more versatile predation strategies, showcasing an escalation in both size and behavioral sophistication. Whereas earlier Triassic archosaurs relied on ambush and brute force, Allosaurus integrated speed, precision, and opportunism, allowing it to exploit a wider range of prey. Its anatomical innovations, from cranial mechanics to limb proportions, reflect a lineage moving toward increasingly complex ecological dominance, a prelude to later giants such as Ceratosaurus and eventually Tyrannosaurus. The evolutionary pressure to optimize both offense and defense is evident in skeletal robustness, claw morphology, and bite mechanics that provided versatility across multiple hunting scenarios. Tooth wear patterns and jaw biomechanics suggest a diverse diet, ranging from juvenile sauropods to smaller herbivorous dinosaurs and even carrion. Analysis of microwear and fracture surfaces indicates repeated engagement with tough hides and armoured integuments, reflecting hunting strategies adapted to forested environments with dense vegetation and mixed prey assemblages. These feeding habits reveal a predator not strictly reliant on any single prey type, but capable of adjusting behaviour to seasonal fluctuations, population densities, and opportunistic encounters. Additionally, isotopic analysis of fossilized bones hints at variable diets across regions, suggesting behavioral flexibility in response to local ecological conditions. Patterns preserved in trackways suggest territorial range, migratory behavior, and possible group hunting strategies. Large sets of parallel tracks imply repeated usage of the same hunting routes, while isolated prints suggest solitary excursions for individual predation or exploration. In some cases, overlapping tracks indicate that multiple individuals may have converged at prey hotspots, hinting at possible social behaviours that, while speculative, underscore the ecological sophistication of Jurassic apex predators. Growth rings in bone histology reveal rapid juvenile development, allowing earlier acquisition of apex predator status. Specimens show accelerated ossification and muscle attachment development, suggesting that Allosaurus juveniles were capable hunters before reaching full adult size. This growth strategy reduced vulnerability to predation and facilitated sustained dominance of prey populations, demonstrating that evolutionary success depends not only on adult form, but also on developmental trajectories and early ecological engagement. The combination of growth patterns, skeletal robustness, and behavioral adaptations illustrates how evolutionary pressures shaped not just adult performance, but life history strategies essential for long-term species persistence. Allosaurus's dominance influenced forest ecosystems, affecting prey populations, vegetation patterns, and interspecies competition. Herbivorous dinosaurs may have altered their feeding strategies, migration, and social behaviors to avoid predation, while smaller predators adapted to exploit niches vacated or created by the presence of such a formidable apex hunter. The cascading effects of Allosaurus's predation created a dynamic web of ecological pressures, where the presence of a single species could shape entire landscapes over millions of years. In its apex role, Allosaurus exemplifies how Jurassic predators perfected the integration of anatomy, strategy, and opportunistic intelligence, foreshadowing innovations in hunting that would later extend into aerial niches. Its reign demonstrates that apex status is achieved through a combination of strength, speed, environmental awareness, and adaptive behavior. From the Triassic floodplains to Jurassic forests, we witness an evolutionary continuum where predators escalated in complexity, setting the stage for theropods that would dominate land for tens of millions of years, and inspiring future evolutionary experiments that would merge predation with flight in the Mesozoic skies. The predator's dominance is not just a matter of size, but of adaptability, a lesson echoed in every subsequent apex hunter that roamed Earth's ancient landscapes. Leviathans of the deep, Tylosaurus. Evolution's pursuit of apex mastery did not end on land. In the depths of the Cretaceous oceans, a predator evolved whose strength, speed, and cunning rivaled any terrestrial hunter. Tylosaurus? A leviathan capable of crushing both fish and rival mosasaurs with precision and power. While forests and floodplains had honed Allosaurus into a deadly force on land, the ocean demanded a new suite of adaptations, and Tylosaurus answered with an anatomy perfectly sculpted for aquatic dominance, where maneuvering in 3 dimensions and responding to currents became a matter of life and death. Its skull, elongated and reinforced, housed rows of conical teeth that curved backward, ideal for gripping slippery prey that could twist and turn in an instant. Each jaw was a lethal combination of force and finesse, able to pierce the hard shells of ammonites, while simultaneously subduing fast-moving fish and juvenile marine reptiles. Fossil evidence shows that some teeth were replaced rapidly throughout life, ensuring that Tylosaurus remained ever ready for combat. Unlike its terrestrial counterparts, this predator relied on a balance of speed and stealth, its body streamlined for minimal drag and maximum acceleration, allowing it to ambush prey from unexpected angles, a skill honed through millions of years of selective pressure. The sinuous tail of Tylosaurus was more than a propulsive tool. It functioned as both rudder and whip, enabling rapid lateral movements and sudden bursts of speed. Muscle attachment sites along the vertebrae indicate a design built for power, capable of turning and lunging with devastating efficiency. In combination with its strong pectoral and pelvic girdles, these adaptations made Tylosaurus an extraordinarily agile hunter, able to strike at prey with deadly precision in both open water and confined reef environments, outmaneuvering competitors and evading larger predators when necessary. Pressure-sensitive nerves embedded along the jaw and skull reveal a level of sensory sophistication comparable to modern sharks. Tylosaurus could detect subtle vibrations and water currents, sensing prey hidden by rocks, vegetation, or murky waters. These acute senses were complemented by large, forward-facing eyes capable of tracking movement across the dimly lit seafloor, suggesting a predator as adept at stealth and strategy as any terrestrial hunter. This acute perception transformed Tylosaurus into a near-perfect ambush hunter, striking with precision even when its target attempted evasive maneuvers, echoing the strategic cunning of Allosaurus, but adapted to a 3-dimensional aquatic battlefield. Growth patterns preserved in vertebrae suggest that Tylosaurus reached apex size remarkably quickly, gaining both length and mass at rates that allowed juveniles to compete for dominance within their ecosystems. By the time it reached full maturity, this mosasaur measured over 12 meters, rivaling the largest marine predators known from the Cretaceous. Such rapid development ensured that Tylosaurus could occupy the apex niche early in life, reducing the window for competition and predation from older conspecifics or rival species, a strategy mirrored in modern sharks, showing that evolutionary solutions repeat across time and environment. Dietary evidence from fossilized stomach contents reveals an eclectic palate. Fish, cephalopods, turtles, and even smaller mosasaurs all fell victim to its predation. Each hunt demonstrates both opportunism and specialization, a dual strategy that maximizes energy intake while reinforcing its status as apex predator. Analysis of wear patterns on teeth and jaws suggests repeated high-force bites capable of crushing bone, while occasional injuries in fossil prey indicate prolonged struggle and complex predation tactics. Through repeated encounters, Tylosaurus shaped the behavior of its prey, influencing schooling patterns, migratory routes, and escape responses, a reminder that apex predators leave indelible marks on the ecosystems they inhabit. Skeletal reconstructions indicate that Tylosaurus possessed strong pectoral and pelvic girdles, providing stability and agility in turbulent waters. Rapid bursts of acceleration could be paired with sharp lateral turns, allowing the mosasaur to intercept fast-moving prey with astonishing precision. These anatomical features reflect an evolutionary trajectory shaped by both predator-prey arms races and environmental pressures, illustrating how apex dominance requires continual adaptation. The creature's vertebral flexibility allowed for sinuous undulations, creating a fluid hunting style that seems almost dance-like, yet lethal in its efficiency. Social dynamics remain less understood, but some evidence suggests occasional interactions between individuals, possibly in contested hunting zones or breeding grounds. Tooth wear patterns hint at intraspecific competition, and overlapping fossil ranges imply territoriality or seasonal congregation. Such behavioral nuances highlight that predation is not merely a mechanical exercise, but a complex interplay of competition, strategy, and opportunity. Mirroring patterns seen among terrestrial predators like Allosaurus. Seasonal aggregation may have also allowed for reproductive synchronization, ensuring genetic continuity in a dangerous and dynamic environment. The oceans themselves created additional challenges and opportunities. Currents, tides, and temperature gradients influenced prey availability, forcing Tylosaurus to adjust hunting techniques or shift territories. Seasonal fluctuations drove migrations of cephalopods and schooling fish, requiring the predator to synchronize its movements with environmental rhythms. These pressures shaped not only its physical adaptations, but also its behavioral strategies, reinforcing the notion that apex predation is inseparable from ecological context. Observing the interplay of predator, prey, and environment highlights the sophistication of marine food webs. Where success requires more than brute force, it demands timing, intelligence, and adaptability. Among contemporaneous mosasaurs, comparisons reveal a delicate partitioning of ecological niches. While smaller mosasaurs specialized in fish or soft-bodied prey, Tylosaurus occupied the uppermost tier, capable of taking down a wide range of prey, including juvenile and sub-adult conspecifics. This hierarchical arrangement minimized direct competition and ensured ecosystem stability, demonstrating that apex predators not only dominate but also structure the communities around them. In this way, Tylosaurus's evolutionary strategy mirrors patterns found in both terrestrial and aerial apex predators, revealing a continuity in nature's solutions to the challenges of dominance. Tylosaurus stands as a model of the evolutionary parallelism of apex predation. Whether on land or in water, success requires a combination of anatomy, sensory acuity, strategic intelligence, and environmental awareness. Its reign in the Cretaceous seas echoes the terrestrial dominance of predators like Allosaurus, but within a medium that demanded entirely different solutions. The predator's mastery is a testament to evolution's capacity for innovation, showing how life repeatedly reinvents the blueprint for apex dominance across every ecological frontier. In the wake of Tylosaurus, the stage is subtly set for semi-aquatic giants that would blur the line between land and water, combining terrestrial strength with aquatic prowess. From the forests and floodplains of Allosaurus to the open oceans of Tylosaurus, the relentless drive toward predatory mastery continues, a narrative of adaptation and power that will next be explored in the colossal, crocodile-like hunters that bridged aquatic and terrestrial realms. Apex of the Cretaceous seas, Mosasaurus. Rising from the currents that Tylosaurus once ruled, Mosasaurus asserted dominance with unparalleled ferocity, stretching over 15 meters in length and towering over nearly every other predator of its epoch. Its sheer size was matched by an agile, hydrodynamic body that combined brute force with astonishing maneuverability, a living testament to evolutionary engineering perfected over millions of years. Fossils from North America and Europe reveal fully ossified vertebrae and elongated paddle-like limbs, adaptations that allowed it to accelerate quickly through open waters or stalk prey along reef edges. Every ripple of its muscular tail generated thrust that could propel it in sudden bursts, granting Mosasaurus a lethal combination of speed and power that few contemporaries could match. Every jawbone reveals engineering optimized for both power and precision, capable of subduing massive prey with crushing efficiency. Its elongated skull housed hundreds of conical, recurved teeth, designed not only to pierce flesh, but also to retain struggling victims within a deadly grip. Biomechanical studies estimate bite forces exceeding 3,000 pounds per square inch, enough to fracture the shells of turtles or tear through the robust bones of smaller mosasaurs. Skull reconstructions indicate flexibility in the quadrate joint, allowing the jaw to open wider than most reptiles, a trait that facilitated swallowing prey whole or in large segments. Such adaptations reflect a predator capable of both strategic ambush and brute force dominance in a highly competitive marine ecosystem. Sleek, muscular flanks allowed sudden bursts of speed, making it a predator of both ambush and pursuit. Unlike Tylosaurus, which relied primarily on stealth, Mosasaurus combined endurance with agility, capable of sustained high-speed chases that could outmaneuver ichthyosaurs and giant cephalopods alike. Its streamlined body minimized drag, while tail vertebrae, reinforced with interlocking chevrons, permitted whip-like motion that could turn the predator into a living battering ram. Fossil trackways and biomechanical modelling suggest it could achieve speeds of up to 15-20 kilometers per hour, remarkable for a creature of its size, enabling Mosasaurus to exploit multiple prey strategies and dominate vast marine territories. Neural canals along the skull transmitted subtle changes in water pressure, granting a sixth sense in hunting that few contemporaries possessed. These sensory adaptations, akin to a lateral line in fish, allowed Mosasaurus to detect the slightest movement of potential prey across tens of meters, even in low visibility waters. This heightened perception likely supported both solitary hunting and interactions with other apex predators, enabling the species to anticipate competitors' movements or avoid larger threats. It is a reminder that predation success relies not merely on size, but on acute environmental awareness and finely tuned sensory systems. Fossilized remains demonstrate an astonishing dietary range, from armored turtles and giant fish to other marine reptiles, highlighting Mosasaurus's versatility as an apex predator. Evidence from stomach contents and coprolites confirms that it did not shy from scavenging or opportunistic attacks on weakened prey. Isotope analysis of bone material indicates consumption across multiple trophic levels, reflecting a predator that adapted its diet seasonally and geographically, exploiting resources wherever they were most abundant. Such flexibility likely contributed to its long-standing dominance and wide paleogeographic distribution. Reinforced cranial architecture allowed jaw rotation and extreme bite angles, expanding feeding strategies beyond any contemporary marine predator. The quadrate squamosal joint permitted controlled expansion of the mouth, while the skull's robust sutures absorbed the immense stresses of struggling prey. CT scans reveal internal reinforcement that prevented cranial fracture, even during high-impact strikes. This combination of strength and mobility made Mosasaurus capable of hunting fast-moving prey like ammonites or ambushing slow, armored creatures without compromising cranial integrity. Early life acceleration in size and mass ensured juveniles could immediately compete for ecological dominance. Mosasaurus hatchlings and juveniles exhibited rapid growth rates, as evidenced by vertebral microstructure, enabling them to quickly reach sizes where predation and survival pressures were minimized. Unlike smaller marine reptiles, which remained vulnerable for years, Mosasaurus juveniles attained significant mass within a few seasons, entering the food chain as formidable hunters and securing their place in the apex hierarchy. Extensive fossil distribution across ancient seaways shows a predator able to navigate multiple marine habitats with expertise. From shallow coastal zones to deeper offshore waters, Mosasaurus remains appear in diverse sedimentary deposits, demonstrating ecological flexibility. Its presence in multiple paleolatitudes suggests adaptations to varying temperatures, salinity, and prey availability, further reinforcing the species' reputation as a dominant and adaptable marine predator, capable of exploiting the full extent of the Cretaceous oceans. Marks preserved on conspecific bones hint at occasional conflict or territory defense among mature individuals. While Mosasaurus was a solitary hunter most of the time, aggressive encounters over prime hunting grounds, mating opportunities, or competition for large prey likely occurred. Paleopathological studies reveal healed bite wounds on cranial and postcranial bones, indicating that disputes were not always fatal but formed part of the species' social dynamics. A reminder that even apex predators faced challenges from rivals. Environmental fluctuations, including shifting currents and prey availability, shaped hunting behavior and migratory patterns. Mosasaurus likely followed seasonal prey migrations, adjusting hunting strategies to align with fish, cephalopod, and smaller reptile populations. Ocean currents and temperature gradients may have influenced long-distance dispersal, as fossil evidence shows the species spanning vast Cretaceous seas. Its adaptability in both physiology and behavior enabled Mosasaurus to maintain apex status despite environmental changes, demonstrating the evolutionary advantage of a versatile predator. Morphological specializations minimized competition with other mosasaurs, carving a unique ecological niche as an apex hunter. Differences in skull shape, tooth arrangement, and body proportions allowed Mosasaurus to specialize in larger prey than contemporaries like Cledastes or Prognathodon, reducing overlap and direct conflict. These anatomical distinctions reflect selective pressures driving diversification among mosasaurs, illustrating the subtle interplay between morphology, behavior, and ecological hierarchy. Mastery of both open oceans and coastal zones made Mosasaurus a predator whose influence resonated throughout Cretaceous marine ecosystems. Its combination of power, speed, sensory acuity, and adaptability ensured that it remained unchallenged at the top of its food chain, shaping prey populations and influencing marine evolutionary trajectories. As Mosasaurus ruled the seas, terrestrial predators were simultaneously escalating in size and complexity, creating a dynamic contrast between land and water apexes that underscores life's relentless drive to perfect predation across every environment. Titanic land hunters, Spinosaurus. Elongated jaws, lined with finely serrated teeth, reveal a predator honed for snapping fish from turbulent currents. Its muzzle perfectly adapted to pierce and hold slippery prey. Fossils from North Africa, particularly the Kem beds, show that Spinosaurus aegyptiacus possessed a skull both narrow and conical, an evolutionary design resembling modern crocodilians yet distinct among theropods. These jaws were not merely for catching fish, they were instruments of precision, allowing the predator to hunt effectively in fast-flowing rivers and shallow floodplains. Toothwear patterns suggest repetitive gripping of prey, while subtle curvature indicates a refined ability to restrain struggling animals, a testament to the evolutionary refinement of semi-aquatic hunting. Spinal sails, towering and membranous, may have served thermoregulatory or display purposes, hinting at complex social behavior that extended beyond solitary hunting. Paleontologists speculate that these sails, supported by elongated neural spines, could have been brightly colored, functioning in mating displays or intraspecific recognition. Beyond display, recent biomechanical studies suggest the sails may have assisted with heat absorption or dissipation, allowing Spinosaurus to maintain optimal body temperatures while alternating between land and water environments. This combination of utility and spectacle underscores the creature's dual role as both predator and ecological signaler, bridging physiology and behavior in ways unseen among other giant theropods. Forelimbs, unusually robust for a theropod, allowed both aquatic locomotion and terrestrial grappling of large prey, revealing an anatomical versatility rarely observed in the Mesozoic. Each arm, equipped with massive, curved claws, could secure struggling fish or small dinosaurs, while also providing stability in marshy floodplains. Comparative analyses indicate that Spinosaurus's forelimbs were stronger relative to its body size than even Tyrannosaurus, emphasizing the adaptive trade-off between power and reach. This combination of limb strength, claw curvature, and muscular articulation provided a biomechanical advantage, enabling it to dominate prey both underwater and along riverbanks. Osteological analysis of limb proportions demonstrates remarkable adaptation for wading and paddling alike, suggesting a semi-aquatic lifestyle that blurred traditional terrestrial and aquatic boundaries. Hind limb measurements reveal relatively short legs compared with other theropods, while the dense limb bones indicate resistance to buoyant forces, allowing controlled submersion. Fossilized pelvic girdles confirm the attachment of powerful muscles capable of propelling the animal through water, giving it surprising agility despite its massive size. The anatomical interplay of limb structure and musculature illustrates an evolutionary compromise, a predator neither fully aquatic nor fully terrestrial, but optimized for hunting across multiple environments. Cranial sensory adaptations suggest the ability to detect minute ripples in water, a semi-aquatic hunting advantage unparalleled among theropods. Isolated fossilized snout bones show the presence of neurovascular foramina, likely housing pressure-sensitive receptors akin to those found in modern crocodilians. This adaptation would have allowed Spinosaurus to locate prey in murky or turbulent waters where visibility was limited. Coupled with keen binocular vision, the skull design highlights a predator that relied on both stealth and precision, capable of exploiting aquatic prey that other large theropods could not. Gut contents indicate a diet heavily weighted toward large fish, with occasional terrestrial prey opportunistically seized, reflecting a flexible and opportunistic feeding strategy. Fossilized stomach remains reveal the presence of sawfish and coelacanth fragments, demonstrating that Spinosaurus was the apex predator of its riverine ecosystems. Yet, bite marks on small dinosaurs and pterosaurs suggest it did not restrict itself to aquatic hunting, instead taking advantage of prey vulnerability along shorelines. Such dietary flexibility not only secured survival in variable environments, but also reinforced its role as a keystone predator within the Cretaceous river networks. Vertebral and pelvic morphology reveal a body capable of both endurance swimming and terrestrial mobility, a rare convergence of locomotor strategies that set Spinosaurus apart from contemporaneous predators. Its vertebrae, elongated and slightly flattened, facilitated lateral undulation akin to modern crocodiles, propelling it efficiently through water. Meanwhile, the pelvis and hind limbs provided sufficient support for movement across floodplain sediments. This dual-capacity anatomy enabled Spinosaurus to pursue prey across multiple habitats, an evolutionary solution to the challenges of semi-aquatic predation. Isotopic signatures in teeth confirm seasonal shifts between freshwater rivers and floodplain habitats, showing flexible hunting ranges that extended across vast territories. By analyzing oxygen isotope ratios, researchers have determined that Spinosaurus periodically moved between river channels and surrounding floodplains, likely tracking prey migrations. This behavioral plasticity would have allowed it to exploit different ecological niches throughout the year, giving it a competitive advantage over purely terrestrial or aquatic predators. Its capacity to integrate multiple habitats into a hunting strategy exemplifies evolutionary ingenuity at the apex of predation. Predation scars on coexisting species illustrate Spinosaurus's role as both predator and ecological regulator, shaping prey behavior and influencing population dynamics. Fossilized remains of large fish and small dinosaurs exhibit tooth gouges matching Spinosaurus's distinctive dentition. These scars provide a window into predator-prey interactions, highlighting not only hunting success, but also the evolutionary pressures exerted on prey species. By controlling populations of both aquatic and terrestrial prey, Spinosaurus indirectly influenced the structure of Cretaceous ecosystems, reinforcing its central role as a keystone apex predator. Reconstructions show a mosaic of rivers, swamps, and forested floodplains, highlighting the complex niche Spinosaurus exploited and the diversity of prey it encountered. Paleogeographic maps and sedimentary analyses depict a semi-tropical landscape where dense vegetation shaded slow-moving rivers, creating corridors for ambush hunting. These environments demanded both stealth and agility, shaping the evolution of Spinosaurus's elongated snout, clawed limbs, and paddle-like tail. Its adaptation to this mosaic environment demonstrates the intricate link between anatomy, behavior, and habitat in achieving apex dominance. Through size, strategy, and ecological versatility, Spinosaurus embodies the pinnacle of semi-aquatic predation, a bridge between water and land that reshaped Cretaceous predator-prey dynamics. In this dual existence, we see evolution experimenting with scale, function, and habitat integration, producing a creature capable of unrivaled dominance. As rivers and floodplains echoed with its predatory presence, Spinosaurus exemplified the ultimate fusion of terrestrial and aquatic strategies, leaving a legacy that continues to fascinate scientists and lay observers alike. Its reign reminds us that apex status is not a singular conquest, but a continuous negotiation between environment, prey, and evolutionary opportunity. setting the stage for reflections on terrestrial giants that would follow in the Cretaceous' southern continents. The pack hunters, Giganotosaurus, and southern giants. Predatory dominance in the southern continents escalated further as Giganotosaurus prowled, its movements calculated with uncanny precision across the Cretaceous floodplains. Towering over the landscape at lengths exceeding 12 meters, this colossal theropod possessed a blend of sheer mass and streamlined agility, allowing it to traverse open plains and wooded groves with startling efficiency. Its elongated skull, equipped with dozens of serrated teeth reaching over 20 centimeters in length, served as a lethal instrument designed for slicing through thick muscle and bone. Fossil evidence indicates that its neck muscles were robust, supporting powerful head strikes capable of subduing prey far larger than a single predator could handle alone. Musculature and skeletal structure reveal a predator engineered for both forceful strikes and remarkable bursts of speed, capable of confronting titanic prey. The hind limbs of Giganotosaurus exhibit a sophisticated balance of length and power, suggesting the capacity to accelerate rapidly over short distances, enabling it to ambush or outpace sauropods and armored herbivores alike. Detailed studies of limb joint articulation indicate flexibility sufficient for agile turns, critical when pursuing mobile prey or coordinating with potential pack members. Its tail, long and muscular, acted as both a stabilizer and a counterbalance during high-speed maneuvers, ensuring that even its immense body could respond with precision. Jaw mechanics suggest a combination of crushing power and slicing efficiency, enabling it to exploit multiple feeding strategies in a single hunt. Bite force estimates derived from computer modeling and comparative analysis with modern carnivorous reptiles indicate that Giganotosaurus could inflict deep, devastating wounds without the extreme bone-crushing specialization of Tyrannosaurus rex. This balance allowed it to tackle both soft-tissue-rich sauropods and more heavily defended prey, leaving behind telltale serration marks that paleontologists have used to reconstruct predatory behavior. Every jaw movement, from the initial clamp to the subsequent shake, reflects a predator refined for efficiency across diverse ecological contexts. Recent discoveries in layered bone beds imply the possibility of cooperative behavior, hinting that these giants may have hunted in packs. Fossil assemblages containing multiple individuals of both predator and prey species suggest episodes of group hunting or at least scavenging events where more than one Giganotosaurus interacted. The spatial arrangement of trackways in these deposits points to synchronized movement, perhaps allowing coordinated attacks on enormous sauropods that would overwhelm a single hunter. Patterns in preserved trackways open a window into locomotion and social interaction, providing clues to group coordination and strategic pursuit. Wide overlapping footprints indicate parallel movement of multiple individuals, suggesting that Giganotosaurus may have patrolled territories in coordinated formations. Trackway spacing, combined with stride length estimates, points to the potential for dynamic positioning during a hunt, with individuals adjusting pace and direction in response to the movements of both prey and companions. Evidence from healed injuries on prey bones supports the notion of sustained attacks, possibly requiring more than one predator to bring down massive sauropods. Marks consistent with repeated slashing and puncturing indicate that individual sauropods survived initial encounters only to face continued harassment, sometimes culminating in fatal outcomes. The frequency and distribution of these injuries suggest hunting episodes of extended duration, where single predators may have coordinated to exhaust or flank their quarry. This form of persistent predation illustrates not only the physical power of Giganotosaurus, but also a level of strategic sophistication rarely attributed to Cretaceous theropods. Biomechanical models show a delicate balance between bulk and agility, illustrating how sheer size did not preclude nimbleness or tactical hunting. Finite element analysis of limb and pelvic bones reveals the capacity to absorb and redistribute forces encountered during high-speed maneuvers or interactions with large prey. Muscle attachment sites indicate rapid flexion and extension, allowing bursts of speed that could surprise even the most cautious herbivore. Sedimentary contexts reveal alternating dry plains and shallow wetlands, each shaping the hunting behavior and territorial range of these colossal predators. Seasonal flooding created corridors of concentrated prey, while dense vegetation provided stalking opportunities for ambush. Analysis of paleosoil and fossilized plant remains informs us about water availability, terrain hardness, and cover, all factors influencing the mobility and hunting strategies of Giganotosaurus. The evolutionary narrative of Giganotosaurus demonstrates a refinement of apex predation, where anatomical adaptation merges seamlessly with potential social intelligence. From the lineage of earlier theropods, this species represents a culmination of size, strength, and behavioral sophistication. Comparative studies with related Carcharodontosaurids reveal incremental modifications in skull shape, dentition, and limb proportions, each contributing to a more effective predatory toolkit. Giganotosaurus illustrates how evolution can sculpt an organism not only for raw power, but also for nuanced ecological interaction, a reminder that apex predators are as much defined by behavior as by anatomy. Examining the interplay of body mass, speed, and hunting strategy, these predators redefine our understanding of Cretaceous ecological hierarchies. Their presence shaped the composition, distribution, and even the evolution of prey species, creating a cascade of ecological consequences across southern continents. Every encounter between hunter and hunted reflects an intricate balance of risk, opportunity, and adaptation, with survival favoring those capable of responding to the complex pressures of a Cretaceous ecosystem. Giganotosaurus exemplifies how apex predation is a dynamic process, continually refined through both evolutionary history and environmental circumstance. In the shadow of these southern giants, the drive toward apex dominance continues to reveal the sophistication and adaptability of terrestrial predation. As the largest predators in their realm, they foreshadow the emergence of later giants like Carcharodontosaurus and even more massive tyrannosaurids, illustrating an evolutionary continuum where size, strategy, and potential social coordination define success. Their reign is a vivid reminder that the path to dominance is rarely linear. It is forged through anatomical innovation, environmental awareness, and the relentless pressure of predator-prey dynamics. From the floodplains of Spinosaurus to the southern plains of Giganotosaurus, the saga of apex predation continues, pointing toward the marine and aerial hunters that would redefine Mesozoic predation. Ice Age predators, short-faced bears, and saber-toothed cats. Vast glacial plains stretched endlessly, challenging every predator that sought dominance over the Ice Age. Across the frozen expanses of North and South America, ecosystems oscillated between seasonal abundance and scarcity, shaping apex predators with extraordinary adaptations. Arctodus simus, the short-faced bear, stood as one of the largest terrestrial carnivores in history, reaching heights of 3.5 meters on its hind legs and weighing over a ton. Its towering frame was matched by limb proportions that suggest remarkable stride length and speed, enabling it to traverse tens of kilometers in pursuit of prey, scavenging carcasses, or patrolling vast territories. Fossil remains from the La Brea tar pits and other Pleistocene sites provide compelling evidence of its dominance, with robust skeletal features indicating a combination of endurance, agility, and sheer power rarely seen in modern mammals. Skeletal reconstructions of Arctodus simus reveal adaptations for both speed and crushing power across open terrain. Long, gracile limbs paired with a lightly built skull allowed this predator to strike a delicate balance between mobility and force. Its disproportionately long legs hint at cursorial capabilities, while the reinforced jaw and thick teeth suggest it could both hunt and scavenge efficiently. Paleontologists have inferred that Arctodus may have been an opportunistic predator exploiting weakened prey or scavenging kills made by other carnivores. The interplay between its anatomy and Pleistocene prey species, like bison, camels, and giant ground sloths, illustrates how evolutionary pressures shaped specialized yet flexible predatory strategies. Smilodon's forelimbs, each a marvel of muscular strength, allowed it to wrestle massive prey to the ground. Fossil evidence indicates that its robust humerus, radius, and ulna could exert tremendous force, stabilizing struggling herbivores while delivering fatal bites. Unlike Arctodus, Smilodon relied on ambush tactics, using dense forests and uneven terrain to approach its prey undetected. Its iconic saber-like canines, reaching lengths of up to 18 centimeters, were remarkably fragile and required precise targeting to the throat or abdomen. Comparative studies with extant felids demonstrate that Smilodon's killing strategy emphasized precision and coordination over prolonged pursuit, reflecting a hunting ecology finely tuned to Ice Age conditions. Fossilized kill sites preserve vivid records of predator-prey interactions, showcasing hunting strategies honed over millennia. Sites in Rancho La Brea, rich in tar-trapped remains, reveal repeated predation events on bison, horses, and camels, demonstrating both opportunistic feeding and repeated selection of high-value prey. Bite marks on bones often correspond to the distinctive morphology of Smilodon's canines or Arctodus's massive premolars, providing insight into feeding behavior and competitive dynamics. These assemblages also hint at occasional encounters between apex predators, illuminating ecological hierarchies and the struggle for limited resources in glacial landscapes. Dental morphology indicates precision in targeting vital organs, emphasizing efficiency over brute force in saber-toothed predation. Smilodon's flattened, blade-like incisors and serrated edges allowed it to sever tendons, arteries, and soft tissue with minimal struggle. This specialization, however, came with trade-offs. The cat's canines were prone to fracture if misused, meaning hunting success depended on stealth, accuracy, and powerful forelimbs. In contrast, Arctodus's dentition was more generalized, capable of crushing bone and consuming a wider variety of food items. Together, these distinctions reveal convergent evolution in apex predators, with different strategies tailored to body design, habitat, and prey availability. Encoded in the isotopes of fossilized skeletons is insight into diet, range, and ecological flexibility among competing predators. Arctodus exhibits isotopic signatures, suggesting wide-ranging omnivory or hypercarnivory depending on region, including potential opportunistic scavenging. Smilodon, conversely, appears more specialized, targeting large herbivores in specific habitats. These chemical tracers also suggest seasonal migration or shifts in foraging behavior, highlighting the dynamic pressures of Pleistocene ecosystems. By combining skeletal morphology with isotopic data, paleontologists can reconstruct not only the anatomy of these predators, but also the rhythms of their daily lives, and survival strategies. Patterns in footprints and skeletal stress point to the limits and capabilities of Ice Age superpredators. Footprints indicate stride length, running speed, and social behavior, while healed injuries on both predator and prey fossils suggest repeated interactions, ambushes, and even failed hunts. Arctodus's long limbs imply endurance for long-distance pursuit, whereas Smilodon's build emphasizes short bursts of power over agility in open areas. Evidence of healed claw and bite marks suggests intraspecific competition or hunting mishaps, underscoring that life at the top was fraught with risk, even for these formidable creatures. Seasonal scarcity shaped social behavior, hunting range, and opportunistic strategies in both bear and cat lineages. Ice Age megafauna experienced dramatic shifts in vegetation, prey density, and climate, forcing apex predators to adapt. Arctodus may have expanded its range or temporarily altered its diet to survive harsh winters, while Smilodon relied on ambush hunting and forested refuges to secure prey. These behavioral adaptations reveal the complex interplay between environment and anatomy, emphasizing that apex predation is a dynamic negotiation, constantly tested by climate and competition. Interactions between apex species highlight competition, coexistence, and evolutionary pressures unique to glacial ecosystems. Fossil evidence shows overlapping territories where Arctodus and Smilodon coexisted, suggesting a delicate balance between direct competition and niche partitioning. Large herbivores bore the brunt of both predators' hunting pressures, with populations influenced by predator density, prey mobility, and environmental constraints. These dynamics exemplify how apex predation extends beyond individual strength, encompassing ecosystem-wide feedback loops that shape evolutionary outcomes. The narrative of Ice Age predation culminates in a nuanced understanding of how apex hunters adapted to environmental extremes. From hypercarnivorous adaptations to specialized killing techniques, these predators evolved in ways that reflect both continuity with Mesozoic megafauna and innovation under new constraints. In examining their anatomy, behavior, and ecological interactions, we gain insight into the final stages of large predator evolution before humans emerged as a transformative force in the ecosystem. In reflecting on these hunters, we see the final evolutionary experiments in apex predation before human influence reshaped the world. The short-faced bears and saber-toothed cats of the Pleistocene demonstrate that apex dominance is never fixed. It is earned through a combination of size, strategy, and environmental awareness. Their reign closes the curtain on a prehistoric saga of predation, linking the grandeur of the Cretaceous and Jurassic titans to the Ice Age landscapes where survival demanded ingenuity as much as power. As the last Ice Age predators roamed, we glimpse the final chapters of prehistoric predation, setting the stage for the emergence of humans into the apex arena, a new epoch in Earth's relentless narrative of survival and dominance. Permian assassins, Gorgonopsids unleashed. Where Ice Age hunters perfected endurance and ambush, Gorgonopsids reveal a more ancient experiment in apex efficiency. Their elongated sabers and agile builds are testament to the innovation of late Permian predation. These terrestrial synapsids, living roughly 260 to 252 million years ago, dominated the dry floodplains and wooded margins of Gondwana and Laurasia, shaping prey populations with a combination of precision, speed, and lethal anatomical adaptations. Unlike later mammalian or dinosaurian predators, their evolutionary design emphasized a balance between piercing force and rapid strikes, allowing them to subdue prey far larger than themselves with a single, expertly targeted lunge. The fossil record, though fragmentary in places, preserves a vivid image of creatures whose form and function epitomize the earliest apex predation on land. Anatomical reconstructions show elongated canines paired with flexible jaws, a lethal combination honed for puncturing, slicing, and maintaining grip on struggling prey. These teeth, some exceeding 15 centimeters in the largest species, were reinforced by robust cranial bones, while musculature attachments indicate remarkable bite force and precise control. The combination of cranial mechanics and saber morphology suggests that Gorgonopsids did not rely solely on brute strength. Instead, they applied a nuanced, targeted approach to hunting, striking vital areas of prey in rapid, decisive movements. Modern biomechanical modelling confirms that this synergy of speed and power was rare in terrestrial predators, giving them a unique advantage over contemporaneous herbivores like dicynodonts and pariesaurs. Etched in sedimented paths, trackways revealed precise stalking behaviour across floodplains and forest margins, revealing an agility previously unseen in terrestrial predators of comparable size. Footprints indicate stride patterns capable of bursts of speed, hinting that Gorgonopsids could ambush or pursue prey over short distances, exploiting both open terrain and the cover of low vegetation. This capacity for coordinated movement likely allowed them to conserve energy between strikes while retaining the flexibility to respond to unexpected prey behavior. Sedimentary evidence shows alternating mudflats, seasonal rivers, and forest patches, which may have concentrated prey in predictable areas, offering opportunities for these predators to exploit both environment and timing with tactical precision. The fine structure of fossil bones reveals insight into growth rates, metabolism, and the life strategies that supported predatory dominance. Cross-sectional analysis of limb and vertebral bones reveals rapid juvenile growth, achieving functional size within a few years, combined with dense cortical bone, suggesting both endurance and strength. Such growth patterns indicate an evolutionary strategy focused on early attainment of apex capabilities, allowing juveniles to compete for prey and territory almost immediately after reaching adult dimensions. These findings contrast with later therapsids, whose slower growth often delayed apex influence, highlighting Gorgonopsids as a model of early predator optimization. In the anatomy of later synapsids, patterns emerge that reveal both convergent and divergent predatory traits, illustrating evolutionary experimentation in early terrestrial carnivores. While some traits, such as elongated canines, appear again in Mesozoic predators and later mammalian saber-tooths, Gorgonopsids combined them with unique forelimb flexibility and skull architecture, emphasizing rapid lateral strikes rather than purely vertical shearing. This combination of adaptations underscores the diversity of evolutionary solutions to the same ecological challenge, securing apex status in competitive ecosystems. Each structural innovation carried functional consequences, shaping predation strategies and influencing prey evolution in ways still observable in the fossil record. Sedimentary evidence paints a picture of resource-rich ecosystems where Gorgonopsids could thrive as top-tier hunters. Layers of floodplain deposits, preserved mud cracks, and ancient riverbeds indicate an environment with abundant herbivorous prey, fluctuating water availability, and opportunities for concealment during hunting. The interplay between predator morphology and habitat constraints likely drove behavioral flexibility, with some species favouring ambush near riverbanks, while others patrolled forest edges for unsuspecting herbivores. By integrating environmental awareness into their predatory repertoire, Gorgonopsids established patterns of apex predation that would echo in later synapsids, archosaurs, and ultimately in theropods. Wear patterns on fossilized teeth hint at dietary breadth, from armored herbivores to smaller vertebrates, demonstrating opportunistic feeding. Microscopic examination of enamel and dentine indicates repeated puncture marks and shearing, implying repeated subduing of struggling prey rather than single lethal bites. This dietary flexibility may have allowed Gorgonopsids to dominate both scarce and abundant periods, a factor crucial for sustaining apex dominance across seasonal fluctuations. By exploiting multiple prey types, they not only secured survival, but also exerted selective pressures that shaped herbivore behavior, anatomy, and population dynamics. Reconstructions of forelimb musculature reveal surprising strength and dexterity, supporting rapid grappling and subduing of prey. The robust humerus, elongated radius, and flexible manus articulate to allow a combination of support, leverage, and striking control, indicating that Gorgonopsids could manipulate struggling animals while delivering lethal bites. Such forelimb capability distinguishes them from later saber-toothed predators, which relied more heavily on head strikes alone, suggesting a more integrated predatory strategy. This integration of limbs and jaws represents a remarkable evolutionary solution to the challenges of terrestrial hunting in the late Permian. Climatic and environmental reconstructions emphasize the challenges of the Permian landscape, shaping hunting strategies and territorial behavior. Periodic droughts, monsoonal floods, and extreme seasonal variability created fluctuating prey availability, forcing predators to adapt rapidly. Fossil evidence of contemporaneous herbivore migration patterns indicates that Gorgonopsids may have tracked seasonal prey movements, establishing territories strategically aligned with water sources and vegetation corridors. By combining morphological specialization with environmental intelligence, these predators ensured their survival and apex dominance in a period of dynamic ecological pressures. In the interplay of predator, prey, and environment, Gorgonopsids exemplify the earliest orchestration of apex predatory dominance. Their combined speed, power, and environmental awareness foreshadow evolutionary trends that would later appear in mammalian carnivores, theropod dinosaurs, and even Ice Age superpredators. By mastering both anatomy and strategy, they created a template for apex predation whose legacy extends far beyond the Permian, echoing through tens of millions of years of ecological experimentation. In reflecting on their reign, we recognize that the patterns established by these saber-toothed synapsids remain instructive for understanding how apex predators continuously shape ecosystems. Reflecting on the shadowed floodplains and forests they once ruled, Gorgonopsids reveal that apex status is never permanent, but always a negotiated balance of anatomy, strategy, and environmental opportunity. From the Pleistocene Ice Age hunters to these Permian assassins, the evolutionary narrative of apex predation demonstrates an enduring, almost timeless drive to master the land. As we peer back into the late Permian, the first true terrestrial superpredators emerged not only as instruments of death, but as architects of their ecosystems, shaping the evolutionary trajectories of prey and future predators alike, leaving a legacy that resonates in every corner of Earth's deep history. Through eons of shadowed waters, sun-drenched plains, and tangled forests, we have walked alongside the hunters that first defined fear and mastery on Earth. Their dominance was never mere size or strength, but a delicate balance of strategy, adaptation, and relentless survival. In their teeth, claws, and silent ambushes, we glimpse the raw, unyielding force of life's pursuit of power. As the echoes of these super predators fade into the fossil record, we are left with awe at the relentless ingenuity of evolution. Join the journey, like, subscribe, and share the story of Earth's first true predators.